This is section 8.4. We have a definition, improper integrals with infinite integration limits. Integrals with infinite limits of integration are called improper integrals. So here we have the integral from a to infinity of f of x. Now we can't really plug infinity in. What we can do is we can approach infinity. So it says if f of x is continuous on a to infinity, then the integral from a to infinity of f of x is the limit as b approaches infinity, and then we'll put b there instead of infinity. So that way we are approaching infinity with a limit. If f of x is continuous on negative infinity to b, then we say negative infinity to b, f of x is the limit as a approaches negative infinity, and we write it like that. If f of x is continuous on negative infinity to infinity, we just have to find a value in the middle that would work nice, and usually we pick 0. Now if we have a function that decreases quickly, then we can have a finite area or an area in which, or a value for the area in which the area will never go over. For example, if this decreases fast enough, maybe the area never goes over 2. So we add on such a small amount that the value never goes above 2. Now if it doesn't decrease fast enough, then we say that the area diverges, and the more area you add on, the bigger the value gets, and it's just headed off to infinity. We say that diverges. Let's see what this says. In parts 1 and 2, if the limit is finite, the improper integral converges, and the limit is the value of the improper integral. So if our function decreases fast enough, we might have a value, and we say that the area converges to that value. If the limit fails to exist, the improper integral diverges. So if you end up with an answer of infinity, we say, well, there isn't an area in which it's converging to, it's just shooting off to infinity. Does the improper integral converge or diverge? If it converges, find the value it converges to. So here's our example. We have integral from negative infinity to 0. So we're going to make, instead of having negative infinity here, we're going to approach negative infinity. We're going to put an a there, and we're going to approach it with a limit. Well, we're going to integrate e to the x, which is e to the x, top minus bottom, so e to the 0 minus e to the a. And e to the 0 is 1, but now we're plugging in negative infinity in for a. And we're doing it as a limit. So, you know, we're still end up plugging it in, but in terms of a limit. Now, that's a negative power, so we can send that to the denominator. So it's 1 over e to the infinity, which is really, now we have 1 minus 1 over infinity, which is 1 minus 0. So that's why we get a value of 1 for this. So the area never gets to 1, but it continuously approaches 1, and it never really gets over that value. What about negative infinity to infinity? Let's take a look at this kind of step by step. So express the improper integral from negative infinity to infinity of e of x dx in terms of limits of definite integrals, and then evaluate the integral. So we're going to write this in terms of limits. Well, first we're going to split this over 0. Now we could split it over any value we want, but 0 seems to be the easiest in most cases. So we have limit as a approaches negative infinity from a to 0, and then limit as b approaches infinity from 0 to b. We integrate. The integral of e to the x is e to the x. Plug in the values, so e of 0 minus e of a, and e of b minus e of 0, and then we end up plugging infinity in. Now this is going to be e to the negative infinity, so that's why we end up having this in the denominator. That'll end up being 0. 1 over infinity is 0. But here's where we run into a problem, right there. E to infinity is infinity, and because of that right there, the value, the integral diverges. It does not converge to a nice value. What do we have here? Evaluating an improper integral on 1 to infinity. So how about 1 over x? So we write it as a limit. Instead of having infinity there, we have a. The integral of 1 over x is the natural log of the absolute value of x from 1 to a. We plug in 1, we plug in a here. That's going to be 0 minus the natural log of infinity, which is negative infinity. That is diverging. It's not converging to a nice value. Well, now we really get into solving these using the different techniques for integrals. So here's a partial fraction example. We can write it as a limit. Limit as a approaches infinity. So instead of having infinity up here, we're writing a. Here's doing the partial fraction part. And it ends up where b is 1, a is negative 1. So that gets us this line right here. And we always like to write the negative one first. Or excuse me, the positive one first. So we have 1 over x plus 1 minus 1 over x plus 3. To integrate, it's the natural log of x plus 1 minus the natural log of x plus 3. We can write that as 1 log using division. And we plug the a's in right here. And when we plug 0 in, we get 1/3. So there's natural log of 1/3. This piece right here is talking about ending behavior. And the ending behavior is the natural log of 1, which is 0. That ends up being negative natural log of 1/3. But we can write 1/3 as 3 to the negative 1. Bring that negative 1 down in front. Negative times a negative is a positive. So if we're doing this, if this is a multiple choice question, the correct answer is probably going to be natural log of 3. This one is tabular. So we replace the infinity with a and write the limit. Here's the tabular piece. Then we can write the integral. Plug in the a's and the 1s. And let's look at this piece right here. Let's look at that piece. It's really negative a over e to the a. Well, think of this as x over e to the x. This is headed to negative infinity, but this heads to infinity much, much quicker. So the overall value of this right here is 0. This one is also 0. And we end up with these two as values, these two right here, which is 2 over e. This one is inverse tangent. But we're going to split it over. We got to pick a value in between negative infinity and infinity. 0 seems to be a reasonable choice. So we integrate inverse tangent, plug in the values right there, 0s and a's. And the inverse tangent of negative infinity is negative pi over 2. So we have negative pi over 2, and the inverse tangent of infinity is pi over 2. So we end up with pi over 2 plus pi over 2 is 2 pi over 2, which is pi. Number 12 is partial fractions again. So here's the partial fraction work. There's where we get the partial fractions. We integrate, which is 3 natural log of x minus 1 minus 3 natural log of x. Plug in the a's, plug in the 2. That's going to be, now this again is ending behavior of that rational function. The powers are the same. It ends up being 1. So we have 3 natural log of 1, that's 0. So we end up with negative 3 natural log of 1/2, but that's 2 to the negative 1. So we bring down the negative, that makes it positive, but then we can bring the 3 up to a power. 2 to the 3rd is 8. Let's look at number 18, tabular again. So another example of tabular. Here's the tabular piece for that. There's the actual integral. We plug in the 0s and the a's. And then, all these a's end up being negative infinity. Well, exponentials increase very quickly. So all of those end up being 0. So the answer ends up being 2. This problem to the right says find the volume if y equals e to the x is rotated around the y-axis. Here is the graph of y equals e to the negative x. And here's the the halfway around, rotating it. And we're going to do this using cylinders so that we don't have to get x equals. So we're going to do shell method. And the area of a shell of a cylinder is 2 pi RH. So there's the 2 pi. The r is the x, the radius is the x, and the height is the function, so e to the negative x. Now we can do this using tabular, right there. I pulled the 2 pi all the way out, and we're going from 0 to infinity, so we want the infinite volume. And we want to see if there is an infinite volume, or maybe the infinite volume just goes to infinity. So we pulled the 2 pi out there, did the tabular work. Here's the integral, and we're going to plug in the a, plug in the zeros. This becomes 0, this becomes 0, and we have a value of 1. So 1 times 2 pi, the volume, the infinite volume, ends up being 2 pi, which means the volume never gets over 2 pi. Students will be able to evaluate improper integrals, same section. Express the improper integral as the limit of definite integrals, evaluate the integral. So here is, there's a rogue limit hanging around there. Let's get rid of this one. I don't know what that was doing there. We change infinity to a, write it as x to the negative 1/3. So it's x to 3/2 times x to the 2/3. Plug in the a's and the 1. But this ends up being infinity when you plug infinity, when you actually evaluate it with infinity. So infinity to the 2/3 is increasing to infinity. This diverges, and there's no value to be had. Well, let's investigate this a little bit more. If you have 1 over x to the 1/3, this diverges, and I show the work for that. You have x to the 1, and this also diverges. But if you have anything above 1, if that power is above 1, then it's going to converge to a value. And you can see when you do the antiderivative, the variable ends up in the denominator. For example, if we have integral from 1 to infinity of 1 over x to the 4th, think about the antiderivative. You have x to the negative 4th, you add 1, well that stays negative, and then you'd have negative 1/3. So the variable ends up in the denominator. So if the variable's in the denominator and we're plugging infinity in for that, that value will end up being 0. The problem over here is when you have x to the negative 1/3 and you add 1, now that power is positive. 2/3 times 3/2. Now you plug infinity in there, and you're going to have a divergent integral. So in general, generally speaking, if you have integral from 1 to infinity of 1 over x to the, let's say, p dx, if p is equal to 1 or p is less than 1, then you're going to have a divergent integral, diverges. If p is greater than 1, that is automatically going to converge, because the variable will end up staying in the denominator. So when you plug that infinity in, all those pieces are going to be 0. Here's a review. Limit as x approaches 0 of 1 over x to the 3rd to the x. The indeterminate form is 1 over 0 is infinity to the 0. So we let f of x equal the function, take the natural log, bring that power down. Instead of multiplying by x, we're going to divide by 1 over x. And we've introduced the limit in there also. We're going to use L'Hopital's. There's the derivative right there. The negative 1 over x squareds cancel, and you're left with 3x to the 3rd. When you plug 0 in, you get 0. But then that's the right side. We got to deal with the left side. There's the limit of natural log of f of x equals 0. Do the e's, and you end up with an answer of 1. E to the 0 is 1. Let's go over to the other one, to the right here. And we replace the infinity with a. We're doing the limit as a approaches infinity, right, is x to the negative 1.1. Now this right here, 1.1 is greater than 1, so this is going to converge to a value. Do the antiderivative. If you add 1 to negative 1.1, when you add 1 there, you get negative 0.1. But then if we were to do the derivative, we would multiply by negative 0.1, so we'd have to cancel that out. So that's where this piece comes in right here. But let's investigate negative 1 over 0.1. If we multiplied the top and bottom by 10, we'd have negative 10 over 1. So that ends up, that piece, negative 1 over 0.1 is negative 10. Well, we're going to plug in the a. We're going to plug in the 1. And negative 10 over infinity to 0.1, that's 0. This piece is 0 plus 10 is 10.